everyone, welcome to the Specialist Maths Units 1 and 2 January lecture. My name is Manjot Bulla and I'll be going through the lecture today. But just before we begin, I'd like to talk to you a little bit about HR Notes. So HR Notes is an amazing company that has, since 2007 been offering heaps of free resources to make sure that all students like yourself can thrive in their studies, and we've offered lectures such as the one that you're watching today since 2015. And the free lectures that we offer are in line with our mission to help students as much as possible so that they can, set themselves up for success throughout their academic journey. And we also offer a bunch of other free resources for everyone. So some of these resources that we offer include study notes, lectures such as the one that you're watching today, online Q&A discussions, engaging online revision videos, newsletters, HR calculator, other articles, and heaps more. So if you're looking to check out some of these free resources to help you out throughout this year, please go to hrnotes.com. And if you require more information or tips on how to use these resources, check out the info doc under the resources section of this lecture page. And if you're looking for even more support, we've got you covered because we offer HR Notes Plus. So basically what HR Notes Plus is, it's sort of like a Netflix type subscription service where you can find a ton of resources. You can find all of our HR Notes books, flashcards, complete course videos, NEEP resources. So it's sort of like a subscription service where you pay a monthly fee and you get full access to all these resources for almost all VCE subjects, as well as year 10 and year 9 resources as well. You can also find a bunch of practice exams, come exam time, flashcards to help you revise for specific topics, and heap more. So I would really encourage everyone to check this resource out. It's honestly life-changing, especially at a VCE level. Okay, so let's get started with today's lecture. But just before we begin, I'd like to talk to you about, who I am. So my name is Manjot Bulla, like I've mentioned before, and I'm a maths and science tutor at TutorSmart, and I've been tutoring for almost a year now. I'm currently studying Bachelor of Biomedical Science at Monash, and I graduated with an ATAR of 99.8. And the subjects that I did throughout VCE were chemistry, maths methods, specialist maths, English, biology, and further maths. So let's get started. Again, just before we begin, I'd like to talk to you about, the subject that you have all decided to do. So if you're a year 10, just watching this video because you're potentially deciding to do the subject, or you're a current year 11 who has decided to pick up the subject, or if you are, thinking of doing the subject and you have no idea what you're doing, this is a great sort of slide for you. So specialist maths, I'm pretty sure, has a notorious reputation of being definitely a challenging subject. So that's probably what you would have heard, but most of the people that have sort of say that probably haven't even done the subject. So there's just sort of like this atmosphere created by students that aren't even doing the subject, that it's super hard, and you're going to get a 20 study score if you pick the subject. That's not entirely true. It's definitely challenging at times, but it's also a very rewarding subject. So definitely a subject that's a bit different to all the other subjects offered at the VC level, but it's definitely a subject that's going to, help redefine, refine your interest in mathematics, if that's something, you're interested in. If you are looking to go into engineering in the future, any form of physics, or even just basic maths at uni level, definitely the subject that you should be doing. It might feel hard currently, well, not even, I wouldn't say hard, but like challenging, it's definitely going to be a very rewarding experience overall if you listen to your teachers, basically all the other things that you would do for your other subjects. So making sure that you're on track, making sure that you ask your tutors, your teachers, anyone you can get help from for help as soon as you feel that you might be a little bit behind or you are not understanding a particular topic. But definitely I would say specialist maths is a really good subject to do, especially if you want to develop that sort of growth mindset and learn how to face challenges more than the content wise, I would say. Because doing specialist maths personally, I felt that it really provided me this with this sort of mindset that I could do something if I tried hard enough. But definitely the content as well is very interesting, very different to the other maths that are offered at VCE, and definitely different to anything you would have done previously in high school. So this lecture is 1 and 2. Just a disclaimer, 1, 2 is actually quite a bit different to 3, 4. And what we mean by different is the topics are quite different. So for example, when you go into 3, 4, you'll find the topics are completely different to what you would have done at 1, 2 level. And this is because what 1, 2 actually does in terms of specialist maths is helps you sort of build a foundation for 3, 4. That's the main purpose of Unit 1, 2 Specialist Maths. It's going to help you learn about the basic foundations of maths, and it will allow you to sort of understand those background skills that we don't even sort of realize we apply when we do maths. So really go into the depth of that so that you can focus on year 12, on the topics in year 12, I should say. And you don't need to worry about the basics or the foundations. So basically 1, 2, although the topics are a bit different, they build a foundation to the abstract mathematical concepts that you will cover in Unit 3 and 4. And 3, 4, if you are interested in doing it next year, will involve focusing on these key topics. So, for example, what you're doing basically this year is, so for example, if we're building a house, what you're doing in Unit 1, 2 is you're building the foundation. So the foundation of the house, and everything that you will learn next year will just build on top of that. So if you are thinking of doing Unit 3, 4, I would definitely say focus on Unit 1 and 2. Don't neglect it. I know a lot of students, what they end up doing is they're probably doing Methods 3, 4 currently, and they're also doing Specialist Maths 1, 2. What they end up doing is they completely focus on Methods 3, 4, ignore Special 1, 2 because they might feel that it's a little bit easy at the Unit 1 and 2 level, and then when they go into Unit 3 and 4, they struggle. Because they haven't focused and haven't consolidated those foundations. And even though the topics won't assess, so the topics in 3, 4 won't assess what you learn in Unit 1, 2, like I said, it's the foundation. If the foundation is not solid, everything sort of just goes into chaos. So really trying to focus on 3, 4, 1, 2 is something I would definitely recommend. And it also gets scaled like crazy, which is probably why half of you have decided to do the subject or not. Personally, the reason I decided to do the subject, and I know it sounds kind of bad, but so it does get scaled crazy, but the scaling is not the be all and end all, I would say. It's definitely more so the mindset that you're going to develop once you start to do this subject. So, here's a bit of an overview of just the subject itself. I know it has changed quite a lot recently due to the new study design. So now that we have a little bit more proof and number, so that is something very new, as well as graph theory and discrete mathematics. So the Unit 1 topics are relatively new, so you're unlikely to find a lot of resources. So specialist maths already is very deprived of resources compared to subjects like methods or chemistry or biology, which have a ton of free resources available online. Specialist Maths doesn't really have a lot of those resources. But do check out the HR Notes resources. We have a ton of those on HR Notes Plus, but just in general, if you're looking for free resources, there's not a lot for Specialist Maths already, and now due to this new study design, there's even less. So I would probably say look through a textbook. That's probably your best sort of resource for Specialist Maths. Ask your teacher for resources. If you have a tutor, obviously they will have resources. Online, I would say not really a lot of resources, specifically for Unit 1, 2. Unit 3, 4, there are some resources, but again, not a lot. So if you are, struggling to find more things to do, or you're struggling to find more practice questions, just ask your teacher, rather than scrolling through, online. So that's mainly what I want to sort of get to is that there's not a lot of resources available for Specialist Maths online. So really trying to use your teacher and your tutor as a resource is really important. In Unit 2, we have data analysis, probability, and stats. Very similar to methods 3, 4 if you're doing that. Space and measurement, trig and vectors, complex numbers, functions, relations, and graphs. So vectors, complex numbers in year 11 will be very basic. And in year 12, you're going to go through it in a lot more depth. But if you're interested or you want to prepare for year 12 Specialist Maths, there's no one stopping you from going into more depth in those topics. But in terms of what the school will assess you on, in terms of what the subject requires you to know, is very sort of surface level, because these are very new topics. You have never done them before. You probably haven't even heard about them before. So for example, complex numbers, when I first learned about it, I'd never heard about them before. So it was definitely very new. And if I had to, do a deep dive in year 11, I would probably blank out. So, so mainly the thing is, everything is very basic, very surface level, just to get you into the mindset required for Specialist Maths. And in year 12, you go through them in a lot more detail and very in depth. But there's nothing stopping you from doing that in year 11 as well, if you want to get a head start. Okay, so let's get started. So what we're covering in today's lecture is going to be number theory and proof. So we won't really have time to cover all of the Unit 1 topics, as this is a bit of a head start. And also we're not going to be looking at a lot of a lot of practice questions. We're not going to be doing a lot of them today. This lecture is mainly just to get you started, get you thinking about what the topics are for Specialist Maths 1, 2, and just to sort of get a little bit of a head start before you begin the school year. Okay, so the first topic that you will cover in Specialist Maths, and I know, just like a disclaimer for everyone, if you don't do this, as soon as you get started on your first day, is because a lot of schools vary the curriculum for Specialist Maths 1, 2, because it is very sort of very varied. So they might do, different topics first and then come back to these topics a bit later on. So you will cover this, but might not just be the first topic that you will cover. Okay, so looking at the first topic, which is number theory. So what is number theory? Well, number theory is the study of integers, basically numbers. So looking at whole numbers, real numbers, all the different types of numbers. And it has a lot of applications in cryptography, crypto systems, all that sort of stuff. There's a lot of applications in those. And some of the stuff in the section will seem like easy math, but like I said, you need to focus on the foundations. This is all building foundations, getting you just thinking about maths in general. So, like I said, some of the stuff in this section will seem like easy math, but what you need to develop is a rigor and formality that is needed for the rest of Spec. So what we are actually learning about is the hierarchy of numbers. So what is the hierarchy of numbers? So up till now, you've probably just heard about, numbers in general. There are different types of numbers. Now we'll actually be classifying those numbers and looking at how we actually use those numbers, for different things in maths. So first we have the natural numbers. So I'll cover them in a little bit more depth on the next slide, but just briefly, natural numbers are basically, another way of saying them is counting numbers. So starting from 1 going all the way to infinity. So whole numbers starting from 1. Just positive numbers. And then integers is where we start to include negative numbers as well. So integers includes everything from negative infinity to positive infinity. So basically every single number, every single whole number. Then we start to get to rational numbers. So these are then numbers which basically fractions, for example, or decimals, stuff like that. Those are rational numbers that we can write as a fraction. So half, 3/4, 1.5, stuff like that. And then we have real numbers. So real numbers are basically all the other weird numbers. So for example, pi, or some of the other ones, for example. And then finally we have complex numbers. Just something really interesting to notice is natural numbers is a subset of integers, and integers are a subset of irrational numbers, and then rational numbers are a subset of real numbers, and then real numbers are a subset of complex numbers. So what that basically means is integers includes natural numbers as well. So just because we say that half is an integer, just because we're saying half is an integer, what it means is that, 1, which is a natural number, is also an integer. Or for example, pi, which is a real number, is also a complex number. So that's basically what it means. So for example, 1 would be an integer, a rational number, a real number, and a complex number, and a natural number. Something like half wouldn't be a natural number, but it would be a rational number. So complex numbers is a big arch of numbers that includes every single number that humans know, basically. And also numbers that humans have created. So complex numbers, I wouldn't really say created, they were forced to create it for a specific reason, and we'll look at that a bit later on. Actually we won't in this slide because it's part of Unit 2, but you will look at complex numbers, really interesting. So here's just a little bit more detail on what they are. So natural numbers, like I said, is a set of positive whole numbers starting from 1. Integers are whole numbers that include positive and negative numbers as well as 0. Then we have rational numbers. So rational numbers only includes numbers that can be written in the form m/n. So also in this slide, we'll be covering a way of how to convert a decimal into this form. So basically anything that can be written as a fraction. So a clear example of something that's not a rational number would be a infinite decimal. So for example, pi, 3.14 something something something. That can't be written as a fraction. But a recurring decimal, so for example, 5.21212121, can potentially be written as a rational number, and that is what we'll be going through a bit later on. Then we have real numbers. So these are all numbers that are possible on the number line, including whole numbers, fractions, thirds, and continuous decimals. And then we have complex numbers. So these are numbers that do not exist on the number plane and include both a real and imaginary component. So I'm not going to go over complex numbers because you will be covering that in Unit 2. Okay, what is a factor? So looking at factors, basically a factor is something that, given that we have two natural numbers, something is a factor if it can be multiplied by something to give us the other number. So for example, 54, if we are asked to, sort of identify if 3 is a factor of 54, we need to find a whole number that multiplied by 3 will give us 54. So in this case, will 54 be a factor of 3? Sorry, will 3 be a factor of 54? My bad. All we need to do is divide 54 by 3 and see if we get a whole number. And 54 divided by 3. So what do we get when we do that? Well, we're going to get 1 and 4. 14 point and a decimal. So it's not a factor. So that's basically what the definition of factor is. Pretty straightforward. You would have heard about, or you would have come across this earlier in high school. Then we have prime numbers. So a prime number is a natural number greater than 1, which only has factors of 1 and itself. So there's a lot of prime numbers, 7, 13, 199. But the formal definition of a prime number is that it's a natural number whose only factors are 1 and itself. So it does not have any other factors. So so we have something called the fundamental theory of arithmetic, which basically has 2 rules. And that basically is that every natural number greater than 1 is either prime, or it can be represented as a product of primes. So any natural number is either prime or can be represented as the product of primes. And when we are representing something according to the fundamental theory of arithmetic, we need to write it in the form basically showing that it's either a prime number or it's the product of primes. So for example, 156, we can actually write as 2 times 2 times 3 times 13. And basically what we do is that's how we write something as a unique product of prime numbers. So a lot of the time you'll get questions where they'll ask you to write something as a product of prime numbers. And the way that I like to do it is I like to start with the number. So for example, 156. And draw something like this. And then right next to it, just write a factor. So for example, I know 2 will be a factor because it's an even number, and then just divide it. So when you divide it, what will you get? You'll get 78. And then do the same division again. So what will be a factor of 78? I know 2 will be a factor again because it's an even number. So dividing it by 2 again, we will get 3, 8. Oh, sorry, my bad. 39. Okay, and then going across 39, I know that 3 will be a factor of 39, so I can divide it by 3. So dividing it by 3. And remember, we're only dividing by prime numbers. There's no point dividing by numbers that are not prime, because remember, we're writing it as a product of prime numbers. So we need to find all the prime factors. That will give us 13. And then 13 is a prime number itself, so we can divide it by 13 again. And we will get 1. Once you get to 1, you can stop. And basically, these are your prime numbers that multiply to give us the particular number. So basically, to write it in that form, we just do 2 times, actually I'm not going to write it again, it's over here, 2 times 2 times 3 times 13. And that's how we write a number as a product of primes. Okay, so remember I said a few slides back that we can convert some decimals into rational numbers. And what are these decimals? Well, these decimals include finite decimals. So finite decimals just mean that they stop. So for example, pi 3.14 something 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 does not stop. It is an infinite decimal. Whereas finite decimal, for example 0.5876, it stops at 6. Those decimals are actually rational numbers, and we can write them in the form m over n. Remember, anything is a rational number if it can be written in the form m over n. And the way that we basically convert a finite decimal into the form m over n is we are essentially trying to eradicate this decimal. So we need to multiply it by a factor of 10, or sorry, not a factor, a multiple of 10 that removes the decimal. So we need to remove the decimal 1, 2, 3, 4 places to make it come over here. So we will multiply by 10 to the power of 4. And whatever we multiply the numerator by, we need to multiply the denominator by that same amount. So therefore you'll end up with this, and then that will equal to 5876 over 10,000. And basically simplifying it, you'll get 1469 over 2,500. That is in the form m over n. So that is basically the easiest method to convert anything into the form m over n, if it is a finite decimal. But what if it is not a finite decimal? What if it's a recurring decimal? So when we're converting something that's a recurring decimal into the form m over n, or the rational number form, we can actually do it. The process is a little bit more complicated though. So basically what we do is, let's just say it's 3 numbers in the decimal place that repeat themselves. So for example, it's 538, then it goes 538, 538, 538. If it's 3 numbers, what we do is we multiply by 10 to the power of 3. If it was 2 numbers, then we'll multiply by 10 to the power of 2. If it was 4 numbers, we'll multiply by 10 to the power of 4. So basically what we want to do is, again, move the decimal place that many places. But this time, instead of getting 0, 0, 0, so for example, if we multiply by 10 to the power of 4, we'll just get 5876.000, right? Here we won't get 0, 0, 0 because it's a recurring decimal, so we'll get 538.538. So after doing that, basically what we need to do is we need to subtract the initial recurring decimal to obtain an integer. So 0.538 times by 10 to the power of 3 minus 0.538 recurring will give us 538. So what do we know now? Well, we know that 0.538 times by 10 to the power of 3 will give us a whole number and a recurring decimal, or an integer, which is 538 if we subtract the recurring decimal. So then what we need to do is we need to divide the integer by 10 to the power of n. So n is whatever you have multiplied to get an integer, essentially, minus 1. And once we do that, we will get the fraction form, because essentially, if you think about it, 0.538 recurring times by this will give us 538. So basically, if we want to write 0.538 recurring as a decimal, we just divide by 10 to the power of 3 minus 1, like this, and that's how we will get it in in the form m over n, or in a rational form. So I hope that makes sense. It's a little bit complicated, but once you understand it, it just makes sense. So basically, we have the recurring decimal, 0.538, and the 538 is repeating indefinitely. How can we change this into an integer? Well, we can multiply by 10 to the power of 3 to get 538.538, 538, 538, 538, so on and so forth. And then to get an integer, all we need to do is we need to multiply by 10 to the power of 3 and then subtract the recurring decimal to give us 538. And then we basically write it in this form. So we know that 0.538 recurring multiplied by 10 to the power of 3 minus itself will give us 538. So to write this in an integer form, sorry, not an integer, in a rational form, we just divide 10 to the power of 3 minus 1, or 10 to the power of n minus 1. If there were 4 recurring decimals, then we would have to multiply by 10 to the power of 4. If there was 2, then multiply by 10 to the power of 2. So on and so forth. Okay, so hopefully you've understand that. And now we'll move on to the next topic, which is proof. So number theory, very small topic, just looking at the hierarchy of numbers, how to convert between, decimals and rational form. Basically, all that sort of stuff is number theory. You obviously are going to go through it in a little bit more depth in class. I'm just going to introduce the topic briefly. So next we'll look at proof. So this is definitely something new in both Specialist Maths 1 and 2, as well as 3, 4. And if you decide to do engineering or maths of any kind at uni, it's definitely something that you'll need. So here it is, and basically this slide will go through what a proof is. So basically a mathematical proof is an argument that demonstrates the absolute truth of a statement. So what are examples of things we might want to prove? Well, we might want to prove that there are infinite prime numbers. So basically anything in maths that we know till now has been proved in the past. And mathematicians, all they do is they prove stuff. So proving is sort of like a mathematical experiment for scientists. That's basically all they literally do. So here is an example of a mathematical proof to prove that 1 plus 1 is equal to 2. As you can see, to prove something even that simple requires so much working out and sort of proof. Obviously, we're not going to understand these symbols, but if you, like I said, if you do math at uni, this is something you'll be dealing with. And it looks a bit ugly, but yeah. We are not going to be doing that at Specialist Maths level. We are going to be doing more chill, more easy, more straightforward stuff. But still, it will be a little bit of a challenge because it's not the conventional sort of maths that you're used to. Getting the answer and that's it. It's more like, how did we get the answer? Or what sort of, not really how did we get the answer, but more like, what process did we follow to get the answer? So the inside workings of our answer. That is what we're going to be looking at. Or basically looking at known stuff, so stuff that we already know, and understanding how did mathematicians initially get to that stage. Okay, so what are some of the principles for proofs? So you need to understand some key terminology. So first, what is a proposition? So a proposition is a statement which is either true or false and is used as a hypothesis in mathematical proofs. So if you do any kind of science, you will be aware of what a hypothesis is. So basically when we're starting an experiment, we need sort of like the question for the experiment. Basically what the experiment will get to, an answer. So if we're doing an experiment involving, I don't know, for example, for biology, we might be doing an experiment involving plant growth. And the hypothesis might be that more sunlight results in more plant growth. That is the hypothesis. Similarly, for proofs or mathematical proofs, we need a hypothesis, a starting statement. And every proposition that we do will have quantifiers. So quantifiers are sort of like the conditions for the proposition, because just having a hypothesis or a proposition will not be sufficient because there's a lot of sort of vague area, or there's a lot of things to experiment with. So a quantifier will state conditions. So for example, if we're trying to prove that 2 plus 3, adding two numbers gives you, an even number, for example, we need to have a condition, because otherwise we have no sort of limitation. We might say adding two odd numbers will give you an even number. Not sure if that works, but yeah. So some sort of condition that we will mainly be focusing on. So there can be multiple quantifiers, but usually you'll be dealing with one quantifier in specialist maths. Okay, so next we have conditional statements. So before proving anything, we will have the conditional. So the conditional, like I basically sort of mentioned, sort of like the proposition, very similar. Basically what it's saying is that if we have something, it implies something. So this symbol, when you're doing proofs, will be very common. So A implies B. So basically what that sort of is saying is, if we know that A is true, therefore we know that B is true as well. So something that will definitely be really common when you're writing proofs, because ultimately what we are proving will have a lot of knowns or givens. So once you've proven something, and something to actually really understand when you're doing proofs is, a lot of the time what you are actually proving might not feel like you're actually proving it at all. So you might be proving 1 plus 2, but what you're actually doing in your working out is proving something entirely different. And then at the end you will say, if we know that this is true, then we know that, this will also be true. So that is what a conditional is. Basically saying that if we know something is true, then something else therefore will be true as well, just through what we have proved. Okay, so next we have different types of proofs. So the first type of proof is the direct proof, probably the most easiest proof that you will do. So basically this involves assuming something is true and then showing that B follows. So for example, if we know that 1 plus 1 is 2, that's actually not a good example. For example, here's a good example. So prove that if W is divisible by 7, W squared is also divisible by 7. So we are assuming straight away that W squared is divisible by 7. And if we're assuming that it's divisible by 7, we have to show that W is divisible by 7. So that is basically our direct proof. So knowing that something is true and then using that fact to prove that something else is true. Next we have negation proofs. So this is basically showing them that the opposite statement is true. So prove for A, B is all integers that 12A plus 18B is not equal to 2. So if we're showing that it's not equal to 2, a negation proof will involve showing that it is equal to 2, or trying to show that it is equal to 2, and then ultimately showing the contradiction. So for example here, we have to prove that 12A plus 18B does not equal to 2. And for the proof, we'll start by assuming that it is equal to 2, and then ultimately show that, mathematically it doesn't work out. So for example, 12A plus 18B is equal to 2. Then we know that 2A plus 3B is equal to 2. Then 2A plus 3B is equal to a third. So 2A, 3B, A and B we know are integers, so 2A and 3B must also be integers. So again, we see that conditional statement. So if we know this is true, then this is true, or this is implied. And then contradiction. So we're showing that two integers, the sum of integers must be an integer. So if we know that A, B is integers, 2A, 3B will also be integers. If we're adding two integers, how are we ever going to get a fraction? So the way that our proof worked was, instead of showing that it is equal to true, is not equal to true, we started by showing that it is equal to true, and ultimately ended up with what we were intending to show. So that is a negation proof. So just reminding you guys of what we've just covered. So direct proof is where we know that something is true, and then we're using that to show something else is true. Negation is where we show the opposite of the statement, and then ultimately getting to the proof that, if the opposite can't be true, then, then what we are trying to show is true. And then we have proof by contrapositive. So sometimes it can actually be really difficult to use a direct proof or a negation proof. In those cases, we actually use proof by contrapositive. So if we are trying to prove that if something is true, then it implies something, what we might actually show is the contrapositive, or the opposite. That if B is not true, then it implies that A is not true as well. So this is actually a little bit of a complicated proof, and you will go through that in a lot of detail in class. And obviously we'll go through tons of examples when you start school, just looking at, how everything works, and how we use all the proofs, when we use them, all that sort of stuff. Currently, we're just looking at the different types of proofs. So we're not going to go through them in a lot more detail, but here is an example that we prove by contrapositive. So prove that for A being an integer, if 5A plus 1 is an odd number, then A must be an integer. Not an integer, an even number. So now to prove the opposite, which is, or prove by contrapositive, what we will start off with is A being an even number. So if A is an even number, or A is not an even number, then then 5A plus 1 is not an odd number. So it's the contrapositive. So the contrapositive statement is, if A is an odd number, so we're saying that it's an even number, now we're saying it's an odd number, then 5A plus 1 must be an even number. So proving by contrapositive. Okay. So here is the proof. Let's just look at it in a little bit more detail. So what we have first done is we have let A equals 2k1 plus 1 for k1 is all integers. So multiplying 2 by any integer plus 1, if we know, so what we are assuming is that A is an odd number. So multiplying an odd number by an even number will give us an even number, plus 1 should give us an odd number. So 5A plus 1 is equal to 2k plus 1 minus plus 1. Sorry, I think that's a typo. It should just be plus 1 here. Ignore that. So 10k1, so we've just substituted what A is. 2k1 plus 1, and we're just letting k1 be an integer. 10k1 plus 5 plus 1, which is equal to 10k1 plus 6, to 5k1 plus 3. So we just simplified that, and let k equal to 5k1 plus 3. So k is equal to 5k1 plus 3. We know that will be an integer because we're only dealing with integers, as k1 is an integer. So 5a plus 1 is equal to 2k, where k is all integers. So that is basically our proof there. So we've basically proven that we've just let k1 be an integer, and we're letting a be an odd number. So 2 times any integer plus 1 will give us an odd number, always, regardless of whether k1 is even or odd. So a we know now is an odd number, and that is what we're trying to prove. If a is an odd number, then 5a plus 1 must be an even number. That is what we want to end up with. 5a plus 1 is an even number. So we've substituted 2k plus 1 for a, and we just basically simplified that. So we get 5a plus 1 is equal to 2 5k1 plus 3. And basically what we've done is, instead of having 5k plus k1 plus 3, we've just let k be equal to 5k1. Just to like sort of simplify it. And then k is equal to 5k1 plus 3, which is an integer. We have to show that it is an integer because we're dealing with integers, as k1 is also an integer. And then finally what we've ended up proving is that 5a plus 1 is equal to 2k. So 2k, so 2 times anything will give us an even number. So therefore 5a plus 1 is an even number, given that k is an integer. So therefore we have ended up proving what we were intending to prove, and using a contrapositive statement has just made it a lot more easier for us. Okay, let's move on to the next topic. Actually, before we begin, I'd just like to let you guys know that I'm actually monitoring the chat, so feel free to put any questions through, and we will have sort of like Q&A time at the end, where you're welcome to ask me any questions, either about specialist maths, or just VC in general, or other subjects. I'm happy to help you guys. Okay, so let's begin. So now we're going to be covering graph theory. So this is actually a new topic as well, and it overlaps with general maths. But this time we're looking more so at the proof side of things. Because remember, an overarching theme of Specialist Maths 3-4 now is proofs and logic. So we'll mainly be covering the basic sort of foundational sort of side of things for graph theory. But in class, you'll be looking at some proofs as well for this, which we won't have time to cover today. Okay, so let's get started. So first of all, what is a graph? Or what is a network? Another name for a graph. Specifically the graph that we are looking for in this topic. So a graph or a network is basically a diagram that will represent the relationships, the connections between objects. So not just objects, it could be people, it could be sort of concepts, it could be literally anything. So it's to represent the relationships and connections that exist between different things. Some key features to note are nodes and vertexes. So nodes and vertexes are the actual objects that, we're trying to represent the relationships between. And then an edge is a line that represents the relationship between the different objects. So this is basically what a conventional network diagram looks like. It's just a lot of dots, which are the vertexes, and then we have edges connecting them. So for example, for this one, we have, and obviously they will have sort of labels. So this might be, a particular city, another city, it just represents the roads between these cities. You'll get all that sort of context in the question. We're just covering sort of like the basics. And just a sort of disclaimer, okay, so another thing to note here is the loop over here. So what is a loop? So loop is basically an edge which connects a vertex to itself. Okay, let's move on. So next, let's look at adjacency matrices. So I'm not sure if you guys have seen matrices before, but you will cover this in this topic, but Also, if you do methods or any other type of maths, matrices you'll cover. So matrices are just ways of representing information, similar to a graph. So a graph represents information, a matrix, just another sort of way of representing information. But matrices are actually very, very useful in mathematics. So if you haven't come across them, you will very soon. Excuse me, guys. So, we have an adjacency matrix here. So an adjacency matrix is actually a special type of matrix because it actually displays the connections of the graph in sort of matrix form. And each node in the graph has been given a letter. Okay, so basically we have rows and columns in the adjacency matrix. And the way that we sort of read the adjacency matrix is, first of all, let's look at just a random sort of number. So for example, this one over here. And it's at the intersection of B and C. So what that basically means is that there is one connection between the nodes B and C. So as simple as that, we are basically sort of looking at the connections and sort of denoting them in the matrix. Okay. Next, we have adjacency lists. Again, very similar to an adjacency matrix. It's to represent the connections between the different nodes. So, the way that we read this is, for example, A, there is an arrow going to B, C, and D. Basically, it shows that A has connections to B, C, and D. An adjacency matrix is actually a little bit more useful because it not only shows you that there is a connection, it also shows you how many connections. So for example, for A and D, there are 2 connections. So there will actually be a number 2 at the corresponding row and column for A and D. Whereas here, we are just writing down what the actual connections are, not giving any indication on the quantity. Okay, so what are the applications of this? Like you will already know, Specialist Maths is all about application. It's learning about the practical skills that will actually be applied in the field of mathematics and physics. So the applications of this topic is, for example, electrical circuits, social networks, molecules, utilities. So obviously there's going to be a lot that you can do with a network. So if you do general maths by any chance, the applications within general maths are a lot different compared to the applications in specialist maths. So application is a dot point in study design. So definitely expect it to be assessed. So just like briefly what those applications could sort of constitute. For example, if we have an electrical circuit, the vertex could represent the wires in the circuit. We could have resistors, voltmeters, all that sort of stuff. So really sort of applicable stuff in real life. So social networks, really common, where we have, individual people, and we are and the lines or the edges sort of represent the accessibility of connections between different people. Molecules, where the vertices represent atoms and the lines represent bonds. Utilities, so house connections to water companies, all that sort of stuff. So, although I said this topic's mainly, again, concerned with proofs, there is sort of like the other side of things where we're just looking at the graph itself and learning how to do maths and interpret these graphs. Okay, now let's have a look at the different types of graphs that you will come across in this topic. So first we have simple graphs. So simple graphs are graphs that have no loops or multiple edges between the same set of vertices. So for example, for A and D, there's only one line that connects them. So there's no multiple edges, so no more than one edge connecting a particular set of vertex. That's basically the only rule for a simple graph. So the second one you can see here, over here, is not a simple graph because it has multiple edges, also has loops. So these are all features that are not common to simple graphs. Then we have isomorphic graphs. So if you do chemistry, you might have heard of isomers or just the prefix iso. So iso just means equivalents or different forms. Different forms of the same thing. So an isomorphic graph has the same connectivity between nodes, although it might be arranged differently. So basically, it's just another way of representing this graph that looks a bit different. And the way that it might be useful is for something called planar graphs. Or for example, maps, a really good application of this. So we might just have a common map, and then we might draw an isomorphic graph just to make the map a little bit more useful. So really, really important sort of stuff. And just a sort of disclaimer for this topic, the length of the lines does not matter most of the time. The length does not matter. So for example, for E and B, this one's short, this one's long, does not matter. It's the same graph. It's an isomorphic graph. It's the connections that we're looking at. Is B connected to E once, twice, or connected or not connected at all? That is what we are checking to see if we have an isomorphic graph, not the actual length of the lines or the edges. Just something a lot of students get confused with. Then we have subgraphs. So subgraphs are smaller graphs that are part of larger graphs. Now, obviously, I can imagine a lot of applications of a subgraph in real life. So for example, if we have, an Australian map, so a map of the entire continent of Australia, and let's just say we only need a map of, the city, Melbourne City, CBD. So that would be a subgraph of the main graph, for example. A very sort of practical example. So subgraphs look the exact same. So we're not drawing isomorphic graphs in this case. We're going to draw the exact same thing, just removing stuff from the original graph. So for example, all of these are subgraphs of this parent graph. Next, we have connected graphs. So connected graphs are basically graphs where we have no isolated vertices. And an isolated vertex is basically a vertex that has no edges connecting it to other vertices. So a connected graph will have no isolated vertices. We will have connections to every single vertex on the graph. And there is a rule for a connected graph. So the number of edges in a connected graph is always equal to the number of vertices minus 1. Sorry, not always. This is the minimum number of edges that we need. The number of vertices minus 1. Any more doesn't matter. Any less, it's not a connected graph. Next, we have complete graphs. So complete graphs is basically a type of connected graph in which every vertex is connected to every other vertex by an edge. So A, for example, would be connected to B, C, D, E. B would be connected to A, C, D, E. So that's why it's called a complete graph. Everything is connected to everything else. It's complete. There can be no further edges added unless we're creating, something that's not a simple graph. So essentially that is what a complete graph is. It's a simple graph where every vertex is connected to every other vertex by an edge. There is a rule to work out the number of vertices in a complete graph. And remember, this is a simple graph as well. So no multiple edges, no loops. So basically, the rule is n minus 1 over 2. So n represents the number of vertices. So to work out the number of edges in a complete graph, all you need to do is take the number of vertices multiplied by the number of vertices minus 1 divided by 2. For example, in this one, instead of counting every single edge, which can get really painful, just count the number of vertices, 1, 2, 3, 4, 5, and apply to this formula. So it will be 5 times 4 over 2, which is 10. So therefore, there will be 10 edges in this graph without counting. Okay, so next we have a different type of graph, which is called a bipartite graph. And this is a type of graph where we have two separate groups of vertices, which have connections between them. So basically, a good application of this is, for example, students and assignment topics. So we have two separate groups. So the first group is student, the second group is assignment topic, and we will have edges connecting vertices from one group to the other group, not within the groups themselves. So we won't have Casey to Alex, but we will have Casey to any one of these assignment topics. So one group to another group, not the same group. So no connections between the same group. Next, we have trees. So trees are a special type of undirected connected graph. Undirected means there's no arrows. So some graphs you will see will have direction. So something like this. A tree will not have any arrows at all. So it's a undirected, connected. So connected, remember, we have no isolated vertices, no loops, no multiple edges, and no cycles. So cycle is basically where we start from one point and end at the other point, covering all vertices on the graph. So if there is a cycle existing in a tree, it is not a tree. So for example, this one, we can start from A, B, C, and come back to A. That's why it's not a tree, whereas this one, it is a tree. Next, we have something called spanning trees as well. So the difference between a tree and a spanning tree is, if this is our parent graph, a tree will include some or all of the vertices. There's no restriction on how many vertices it has to include, but it's sort of like a subgraph of the original graph, including some or all of the vertices. Whereas a spanning tree will include all of the vertices, and usually the application of spanning tree is, let's just say, this is sort of like a map, and we want to work out the shortest paths between these different locations. Let's just say we have distance as well. 4, 2, 3, 4, 5, 6, whatever. And let's say we have multiple edges like this. This is an original graph, so it can have multiple edges, but the tree will never have multiple edges. Just like this, and let's say it has a length of 3. So if we're trying to create a spanning tree, essentially what we're trying to do is select the edges that have the lowest weight, usually. But just in general, what we're looking at in terms of specialist maths, mainly, a spanning tree will include every single vertex of the parent graph, whereas a tree will only include some of the vertices of the parent graph. As you can see here, it only has A, C, B, A. This one has all of them. Okay, let's move on. Next, we have regular graphs. So a regular graph is basically a graph where each vertex has the same degree. And what is a degree? Well, a degree is basically looking at the number of edges going out of one vertex. So for example, A, we have 1, 2, 3 edges coming out of it, so we say that it has a degree of 3. In a regular graph, all vertices have the exact same degree. So for example, this one, everything has 3 connections. So 1, 2, 3, 1, 2, 3, 1, 2, 3. So as you can see, it will be a regular graph. And a specific name for this particular type of regular graph would be the 3 regular graph. So the naming scheme here is we look at the vertex, the degree of each of the vertex, and since in a regular graph it will be the same, we just call it a K regular graph, or a 3 regular graph, or a 2. I think a 2 regular graph will exist. Technically it could. A 2 regular graph, or a 4 regular graph, so on and so forth. So we will name the graph, the regular graph, depending on the degree of the vertices. Then we have platonic graphs. So these are a type of regular graph which represent the skeleton of a platonic solid. So what is a platonic solid? So a platonic solid is sort of like a three-dimensional solid. For example, like this, a tetrahedral graph, an octahedral graph, a cubical graph. So basically something that has the same base on each side. So for example, it's triangles on each side. If it's squares, it's squares on each side. If it's, what is this? A pentagon, it's pentagons on every single side of the object. And as a result, this can also be represented as a regular graph. So these are all regular graphs. So we can represent platonic solids as regular graphs. And if we do, in that case, we call it a platonic graph. So it's a two-dimensional version of the solid. That's essentially what a platonic graph is. A two-dimensional version of a three-dimensional object. Okay, so next we have something called the handshaking lemma. So this is sort of when we're getting into proofs. So the handshaking lemma is basically a statement or a mathematical statement that the sum of the vertex degrees is always equal to double the number of edges in the graph. So if the sum of the degrees in a graph is 10, then the number of edges in the graph will be double that. It will be half of that. So 5. So we will have 5 edges if the sum of the degrees is 10. So in this graph, we will have the degree of A is 6, the degree of B is 5, and then 4, 2, and 1. And if we add them up together, we will get 11 plus 4, 15, plus 3, 18. So therefore, we will expect 9 edges on the graph, according to the handshaking lemma. And indeed, that is the case. So we have 1, 2, 3, 4, 5, 6, 7. Sorry, how do I count this? 1, 2, 3, 4, 5, 6, 7, 8, 9. As you can see. Just another note that I want to make, a side note, is a loop actually contributes to 2 degrees. So although it's the same edge recurring on the same vertex, so let's say if we're looking at it from this side, this edge just looping back to the same vertex, it actually contributes to 2 degrees because we're looking at how many connections are going out of the vertex or into the vertex, depending on how you want to see it. So that is why the degree of C is 4, but the degree of E, for example, is still 1 because we don't have any loops. Okay, so now we have planar graphs. So planar graphs are a type of isomorphic graph that can be drawn without any edges overlap. So basically a graph which we can redraw as an isomorphic graph where none of the edges are overlapping. So remember from a few slides back, an isomorphic graph is a graph that has the same connections but looks a bit different. And a planar graph is basically a graph where an isomorphic graph or a similar graph exists where the edges do not overlap. So for example, this one, if we take this edge out and draw it like this, such as down over here, and also this one over here and draw it like this, we get an isomorphic graph. It's called an isomorphic graph because it's the exact same graph, just different look to it. The connections are the exact same, the degrees are the exact same. And here we have no edges overlapping, so we call this a planar graph. So a lot of the time you'll get questions like, is this a planar graph? And you'll get this graph over here. So right now, currently you can't tell, so you have to draw the isomorphic graph. And if you can't find any way of drawing the graph without having the edges overlap, then it is not a planar graph. So it's a little bit of trial and error when it comes to these sort of questions. Oops. Okay, so then we have Euler's formula. So, Euler's formula is basically, again, a proof. A proof that something is a... sorry, what was I going to say? Oh yeah, so it's a proof to show that something is planar, or a graph is planar. And the way that it basically works is we have a planar graph, and the Euler's formula is that the number of vertices plus the number of faces minus the number of edges should be equal to 2 in order for a graph to be a planar graph. And we can only work out the number of vertices, faces, and edges if it's in the planar form. So for example, for this one, where the edges are overlapping, we can't work out the number of faces. And just before I get started on what a face is, it's just basically, before I get started on the Euler's formula, a face is basically the enclosed regions within the graph. So for example, this is a face over here between A, B, and D. This is a face between A, C, D, B. This is a face between E, D, C. And this is actually also a face. So we consider the outside region as a face as well. But if you look at this graph, which is not planar, oh well, technically it is planar, but just hasn't been drawn in the planar form, we will technically count it as 1, 2, 3, 4, 5, 6, and 7 faces. So that's where we make our mistakes. It's really important to convert the graph to planar form before proving using the Euler's formula that it is planar. And basically all we need to do is we need to sub in the information into the formula. So the number of vertices, so 1, 2, 3, 4, 5, plus the number of faces, so we just have 1, and remember the outside region is also a face. So 1, 2, minus the number of edges, 1, 2, 3, 4, and 5, is equal to 2, as stated. So therefore, this graph would actually be considered as a planar graph. Okay, next we have some traveling problems. So traveling is basically when we're looking at sort of more the map side of things for networks. So like I said, a network can be represented as sort of like a map. So when we are basically representing these types of graphs, we can also have different types of ways in which we can navigate through that network. And these can be in the form of walks, trails, circuits, paths, and cycles. And all of these have different sort of classifications. So a walk is basically when we have a sequence of edges that link with vertices. So starting at one point and then going to another point. Walk is basically the simplest type of sort of movement, and literally everything classifies as a walk. So walk is sort of like the generalized term for a sequence of, basically a sequence going through a network. Next we have trail. So trail is a little bit more of a specified type of walk. So it's a walk where we are not repeating any of the edges. So I'll go over what all of that means in a second, but I'll first just like to explain what all of these are. Then we have circuits. So circuits are a type of trail in which we start and end at the same vertex. So we start at one point and we end back at the same point, but we're not repeating any edges. A path is a specialized type of walk where no vertices are repeated. So trail, no edges. Path, no vertices. But technically, you're not repeating any edges either. So for a path, if you're not repeating any vertices, how can you repeat an edge? So basically, you can sort of say it's a specialized type of trail where we're not repeating any vertices. But anyways, and then we have cycles. So a cycle is a type of path, essentially, where we start and end at the same vertex. And we are not repeating any edges or vertices. Okay, next we have specialized types of trails and circuits. So, first we have Eulerian trails. So it's a special type of trail. And in this trail, we must visit every single edge in the network diagram exactly once. And following all the other rules of trail, which is not repeating any edges. So therefore, the only special rule here is that we must visit every edge. But for just a normal trail, there's no sort of rule that we have to visit every single edge. But for Eulerian trails, we do. And an Eulerian trail will only exist if a vertex has an even degree, except exactly two vertices which have an odd degree. So for an Eulerian trail to exist even, all the vertices need to have an even degree except for exactly two which have an odd degree. That's the only way for an Eulerian trail to exist. Then we have Eulerian circuits. So Eulerian circuits being very similar to an Eulerian trail, but must start and end at the same vertex. And in this case, in order for an Eulerian circuit to exist, the degree of all of the vertices in the network diagram must be even. Okay, next we have Hamiltonian paths. So Hamiltonian paths are a special type of path in which every vertex must be visited exactly once. So we need to pass through every vertex on the network diagram exactly once. So for a normal path, there was no rule on that. For a Hamiltonian path, we need to go through every single vertex. Hamiltonian cycle, similar to a path, visiting every single vertex without repeating any vertices, but we now must start and end at the same vertex. So those are all the specialized types of paths, cycles, traveling sort of situations. Here's just sort of like a summary table to summarize what they basically are. So walks, can use edges more than once, can use vertices more than once, do not have to start and end at the same vertex, and can start and end at the different vertices. So it doesn't mean a walk can't start and finish at the same vertex. It can. It doesn't have to. And so on and so forth. So a really good summary table, just having your bound reference, or just at the back of your notebook somewhere. But let me just quickly go through what I mean by a walk or a trail. So basically you'll get something like this, and you'll be asked to identify a walk. So walk will literally just be DAC, that's a walk. EBC, that's a walk. EB, that's a walk. And then a trail, a walk with no repeated edges. That could be, for example, DABE. We haven't repeated any edges. A circuit. That could be something like ACB. ACBA. That's a circuit. A path. Walk with no vertices are repeated. DACBE. No vertices are repeated. So that's essentially what you'll be asked to do. So identify the actual sequence. Eulerian trail, Eulerian circuits, Hamiltonian paths, Hamiltonian cycles, a little bit more specialized. And remember, for an Eulerian trail to exist, only two of the vertices can be odd. So in this case, we have 1, 2, 3, more than 2 vertices which have an odd degree, which means that neither can an Eulerian trail nor an Eulerian circuit can exist. So they don't always have to exist. What about a Hamiltonian path? That is a little bit more trial and error. We just have to work it out and see if it works. A Hamiltonian path, yes, I think it will exist. So DACBE. And remember, there are multiple alterations to this. There's not just one clear answer. But a Hamiltonian cycle will not exist, because if we start at, for example, A, we go D and then we have to come back. Or we start at D, A, we can't come back to D without repeating any edges or vertices. So basically that is what this topic sort of really revolves around. But yeah, that's basically it for this lecture. There's not a lot in terms of content that we need to go through. So now we'll just actually go through some practice questions to consolidate what we've learnt in terms of graph theory, and also just the rest of the concepts covered throughout the lecture. So let's get started with the questions. So the first question, Consider the following graph. Which one of the following statements is not true for this graph? Okay, so what do we have here? We just have sort of like a basic sort of connected graph. Let's read the options that are given. So this graph has 7 vertices. Let's count them. 1, 2, 3, 4, 5, 6, 7. That is true. And we're trying to find the not true statement. So A is not the answer. There are no isolated vertices. That is actually true. So remember, isolated vertices are vertices that are not connected to any other vertices by edges. As in the name suggests, they're basically isolated. And we have none of them here. All vertices have an even degree. Okay, let's have a look at that. So this has a degree of 2. Remember, degree is the number of sort of connections that a particular vertex has with other vertices or to itself. Basically the number of lines or edges going off of it. That's the way I like to think of it. So this has a degree of 2, 2, 2, 4, 2, 2, 2. So all of them are even. So that's true. 6 of the vertices have the same degree. Yep, 2, 2, 2, 2, 2, 2. Yep, 6 of them have the same degree of 2. The sum of the degrees of the vertices is 14. Okay, let's count them. So 2, 4, 6, plus 4, 10, 12, 14, 16. Yep, so that's our answer. The sum is actually 16, it's not 14. The adjacency matrix for the graph above with nodes as labeled is, okay, so we are trying to work out the adjacency matrix for this graph. Remember, adjacency matrix is basically a matrix representation of a graph. And the way that we sort of look at it is we assign the rows and the columns with numbers. So they haven't labeled it for us. I'm just going to label one of them just so everyone knows what's going on. So we have 1, 2, 3, and 4. And basically we're just looking at the connections and seeing whether, how many connections there are, whether they are correct. So let's just pick a random sort of vertex. So let's just pick this vertex over here, which is vertex 1. It has connections to vertex 2, one connection to vertex 2. So in the intersection between 1 and 2, there should be a 1. And there's not a 1 here. So therefore C is actually not the right answer. So we need to have a 1 here at the intersection of 1 and 2, because 1 and 2 have one edge that is connecting them. So if there is a 0 in that spot, it's not the right answer. Yep, so we want a 1 here and a 1 here. So it's either A or B. Let's just pick another random point. So let's actually look at the difference between these two answer options. And the difference lies over here between 1 and 1 in itself. So is there any loops here for 1? And the answer is no. We don't have any loops. We don't have any edges that just connect 1 to itself. Because we have 1 connecting to 2, 1 connecting to 4, and 1 connecting to 4. So there shouldn't actually be a 1 here. So therefore our correct answer is actually B, in terms of finding the adjacency matrix. I hope that makes sense. Let's move on. Okay, consider the following graph. The adjacency matrix for this graph with some elements missing is shown below. Okay, this adjacency matrix contains 16 elements when complete. Of the 12 missing elements, and then we're just sort of filling the blank type of thing. So let's just actually fill out the adjacency matrix before we go on to find the correct answer. That's probably the best method of doing it. So we're trying to find what goes here, and remember, looking at the intersection point. So X and W. So we're looking at how many connections there are between X and W. So there's actually 1, and we're looking at direct connections only. Because obviously there are second degree connections as well. So you could do, Y, X. We're not looking at those. We're just looking at direct edge connections. Oops. So we have 1 and 2 connections between W and X. So there should be a 2 here. Next, looking at this one, which is W and Y, we have, again, 1 and 2 connections between W and Y. So a 2 goes here. And next, looking at W and Z. W and Z. Well, there is just 1 connection. So we can just write it there. And the thing about adjacency matrix, the rows are actually the exact same as the columns. So this is actually also going to be 2, 2, 1, because now it's just, sort of flipped. It's the exact same thing. Okay, now let's move on to the X row. So looking at the connections with X. So X has, and if you want to tell if you've done it correctly, just look at how many edges are going off of, a particular vertex. We have 1, 2, 3, 4, 5, 6, 7. And if this equals to 7, then we have done it correctly. 1, 2, 3, 4, 5. Oh, sorry, just realized this is the same edge. It's a loop. So 1, 2, yep, so it should just be 6, not 7. My bad. Okay, next looking at X. So X has 1 connection to Y and 1 connection to Z. Pretty straightforward. So we also fill out the vertical as well. So 2, 0, 1, 1. Next, looking at Y. So Y and Z. Y and Z, only 1 connection. Like so. And Y and Z, 1 connection. And then we're done. So that's all we had to do in this case. So the adjacency matrix, so of the 12 missing elements, 8 are 1 and 4 are 2. So we have 1, 2, 3, 4 2s and 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9 1s. So it's not A. 4 are 1 and 8 are 2. 6 are 1 and 6 are 2. 4 are 0. 4 are 1 and 4 are 2. So we already know that we have 4 2s. So we can already cancel our stuff where it's more than 4 2s. We cancel out this. So out of these 2, sorry, I think I miscounted. Oh, sorry, I counted this one as well. So it should just be 1, 2, 3, 4, 5, 6, 7, 8. Oh yeah, so that one's actually correct. I think I miscounted that one before. Just rub that out. Okay, let's move on. Again, if you have any questions whatsoever, just pop them into the chat and I'll be monitoring the chat, so I'll answer them as the questions come in. Okay, Euler's formula relating vertices, faces, and edges does not apply to which one of the following? So, Euler's formula, does anyone remember what that was? So if you do, pop it into the chat. But going back a few slides, Euler's formula is the formula where we basically have a planar graph and we're using the Euler's formula just to prove that it is a planar graph. But if something we know is a planar graph, we can also use it to find the missing number of vertices, the missing number of faces, the missing number of edges. So just quickly recalling what the Euler's formula was, it was vertices plus faces minus edges equals to equals to 2. That's basically the Euler's formula. So if you have one thing missing, for example, you don't know the number of edges, you can use the number of vertices, faces, and this formula to work out the number of edges. That can work for any one of these. But this question, what we are actually doing is seeing which one does it not apply to. So basically we're trying to work out which graph is not planar. Remember, Euler formula only applies to graphs that are planar. And how can we determine that? Well, we can determine if a graph is planar if we can basically draw an isomorphic graph for a particular, a graph that does not look planar. Just to recall, planar means that we have no edges that are intersecting each other, at points that are not vertices. So for example here, currently this graph does not look planar. But if we redraw this edge, so get rid of this edge and redraw it, now that it's planar, we have nothing that's that is intersecting other edges. What about this one over here? Can we redraw it? A little bit difficult to see here, but basically what we can do is move this vertex over here, and that basically solves the problem. And then we'll have this, this, and this. And that basically solves the entire problem. What about this one over here? What's intersecting? Oh yeah. Basically this one is intersecting with this one and this one. Okay, so there's a really easy solution for this one as well. Basically what we can do is move, this vertex outside over here. And then we can draw connections to it like this, like this, like this, 2, 3, 4, and like this. That way we have no intersections, and that's all fixed up. So that's also planar, this is planar, this is planar. What about this one? This one is also planar, because basically what we can do is just redraw this edge like this, redraw this edge like this, and basically we've solved the issue there. So this one's planar as well. This one, you can already tell it's sort of not planar. It's really difficult to redraw, because we can redraw this edge, for example, like this, no problem. What else is intersecting? This one we can redraw like this, no problem. Now when it comes to redrawing this edge over here, if we had to redraw like this, now the edges are intersecting, so there's actually no way of redrawing this graph to make it planar. So therefore this is our correct answer. So in this question, the examiner's being really indirect, or your teacher, whatever. So if you get a question like this, although it's technically asking for Euler's formula, what it is actually assessing is your ability to draw isomorphic graphs, your ability to understand what the Euler formula can be applied to, which is planar graphs, and also your ability to recognize planar graphs. So testing a variety of skills here, but in a sort of an indirect way. Okay. Bus routes connect 6 towns. The towns are North End, Opera, Palmer, Quigley, Rosebush, and Seatown. The graph below gives the cost in dollars of bus travel along these routes. Bai lives in North End, and he will travel by bus to take a holiday in Seatown. Euler's formula V plus F equals E plus 2 holds for this graph. Complete the following by writing the appropriate number in the boxes provided below. So this is a pretty straightforward question. We know the Euler's formula, we're just applying it to this question and just showing the examiner we know what a vertex is, we know what a face is, we know what an edge is. So first of all, how many vertices are there? So there's 1, 2, 3, 4, 5, 6 vertices. What about the number of faces? Well, remember, faces are the enclosed regions between edges and vertices. So we have 1, 2, 3, 4, 5, 6, and we also count the outside region as a face, so 7 faces. What about the number of edges? There is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 edges. So that all makes sense. That cancels out. So we know that we've done everything correctly. Okay, next question. Which one of the following, and also while I'm doing these questions, if you're watching this lecture live or you're watching the recording, please make sure to actually pause when I get to a particular question, attempt it yourself, and then watch the solution. Because specialist maths is a subject that requires you to have a lot of practice, so really start to get all your practice in, from the beginning. Don't wait till, it's exam time or SAC time. Okay, which one of the following graphs contains an Euler circuit? So, when did we say an Eulerian or an Euler circuit existed? Well, we said that an Eulerian circuit only existed if all of the vertices had an even degree. So we're just basically trying to find out the graph that has all edges being of even degree. So A, we can clearly cancel out because this one has a degree of 1, which is odd. This vertex has a degree of 3, so we can cancel that one out. This one looks correct. Oh, never mind. This one has a degree... Oh, sorry, never mind. It does have a degree of 4. I thought this was just these 3. Anyways, this one looks to be the correct answer. But let's look at the other ones. Oh, this one has a degree of 3. Not the right answer. And this also has a degree of 3, so not the right answer. So indeed, our answer is C. Oops. Okay, moving on. Here we have a short answer question. Aiden, Braden, Carey, and Dunlop, Edwin, and Farnham are 6 towns. The network, or the graph, shows the road connections and distance between these towns in kilometers. How many different ways are there to travel from Farnham, to Carey without passing through any town more than once? Okay, so what we are trying to do is find a route from Farnham, which is over here, to Carey without passing through any town more than once. This one sort of trial and error, I would say, just like, work out all the different ways and just sort of figure it out. So the first way is 1, 2, like that. Then we also have 1, 2, 3. That's another way. What about 1, 2, 3, 4? That's another way. So currently we have 3. Next we have 1, 2, 3, without passing through any town more than once. Oh, okay, so we can't pass through any towns more than once. That's all good. I was just checking this one. Oh yeah, that one's good. This one. Okay, so we have 4 in total. So the first one is like this. Second one is like this. Third one is like this. And the fourth one is like this. So 4 in total. Yeah, I can't see any other ones. If you have spotted another one, just let me know in the chat. Okay. An engineer plans to inspect all the roads in this network. He will start at Dunlop and inspect each road only once. At which town will the inspection finish? Okay, so start at Dunlop and inspect each road only once. So it's visiting every single edge exactly once. And we're trying to work out which town will this inspection finish. So what is this? This is actually an Eulerian trail, if you think about it, because you're passing through every single edge. You're not repeating any edges. You can repeat vertices, doesn't matter, but you're not repeating any edges. And you're starting from one point and ending at another. So it's an Eulerian trail. And remember, an Eulerian trail starts at one vertex, which has an odd degree, and ends at the other vertex, which has an odd degree. So Dunlop has an odd degree. So what's the other vertex that has an odd degree? Well, it's this one over here, Breeden. So that is where he will be finishing off. And obviously you can do a bit of trial and error, but this is the best method. For Eulerian trails, you start at one odd vertex and end at the other odd vertex. So that's why we need two odd vertices for a Eulerian trail to exist. But for Eulerian circuits, it needs to be all even degree. Okay, another engineer decides to start and finish her road inspection at Dunlop. Okay, if an assistant inspects two of the roads, this engineer can inspect the remaining 6 roads and visit each of the other 5 towns only once. How many kilometers of road will the assistant need to inspect? Okay, let's see. Another engineer decides to start and finish her road inspection at Dunlop. If an assistant inspects 2 of the roads, this engineer can inspect the remaining 6 roads and visit each of the other 5 towns only once. Okay, so again, we're starting and ending off at Breeden, but this time we're not visiting all the other vertices. So the main sort of way that I can think about it is, sorry, let me just read this one again. If an assistant inspects 2 of the roads, this engineer can inspect the remaining 6 roads and visit each of the other 5 towns only once. How many kilometers of road will the assistant need to inspect? Okay, so it doesn't give us any indication on whether the other engineer needs to start or end at a particular spot. It just says that it's going to inspect 2 of the roads. And the engineer will inspect the other 6 roads, starting and ending at Dunlop. So what are the ways in which we can visit 6 vertices starting and ending at Dunlop? Well, we can go like this, like this, like this, and this. So what is that? 1, 2, 3, 4, 5, 6 roads. That's probably the only way in which we can do this. Otherwise, we can do, like this. 1, 2, 3, 4, 5. That's 5. 1, 2, 3, 4, 5. Again, doesn't work. So this is the only possible way. So therefore, the 2 that the assistant will inspecting will be these 2 over here. So this one and this one. So just totaling it up, it will be 240 kilometers. Okay, let's move along. Again, if you have any questions, please pop them into the chat. Okay, water will be pumped from a dam to 8 locations on a farm. The pump and the 8 locations, including the house, are shown as vertices in the network diagram below. The numbers on the edges joining the vertices give the shortest distance in meters between locations. Okay, question AI. How many vertices on the network diagram have an odd degree? This one's a bit of an, just a basic question, just counting the number of vertices with an odd degree. So this one, even, has a degree of 2. This one, 1, 2, 3, 4, even, 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 1, 2, 3, 4, 5. Oh, okay, this one's odd. 1, 2, 3, 4, 5. This one's odd. 4, even, and even. So, 2 vertices. The total length of all the edges in the network is 1,180 meters. A journey starts and finishes at the house and travels along every edge in the network. Determine the shortest distance traveled. Okay, so we're starting and ending at the house. So basically what we are doing is sort of like an Eulerian trail where we go, across through all the edges, and then there's one that we need to repeat. Which one will that be? So if you think about it, what is an Eulerian trail? An Eulerian trail is one that starts at one odd vertex and ends at the other one and visits every single edge exactly once. So therefore, in this case, if we are trying to visit every single edge, but then so let's say we start at the house, we will end at this one, and we would have traveled 1,180 meters. But we also need to come back to house. So therefore, we'll need to travel on this edge one more time. So therefore, the distance that it will travel will be 1,180. So that's the total distance of all the edges combined, plus that extra 70 just to get to home base. So therefore, our answer here will be 1,250. Yep. Okay. IV, a Hamiltonian path beginning at the house is determined for this network. How many edges does this path involve? What is a Hamiltonian path? Well, a Hamiltonian path is basically something that's going to visit every single vertex exactly once. So what could be a possible one? Let's just have a think about that one. So let's just say we are starting at the house and we need to visit every single vertex. So we need to go to this one, 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 this one. Okay, so that's basically the Hamiltonian path. We visited every single vertex. So what is that? What is the number of edges here? So it's 1, 2, 3, 4, 5, 6, 7, 8. So regardless of how you actually do this question, your path might look a bit different. The ultimate answer that you're going to get is going to be 8. Okay. This question over here. Maggie's house has 5 rooms, A, B, C, D, and E, and 8 doors. The floor plan of these rooms and doors is shown below. The outside area F is shown shaded on the floor plan. The floor plan is represented by the graph below. On this graph, vertices represent the rooms, and the outside edges represent direct access to the rooms through the doors. One edge is missing from the graph. Okay, so question C. Maggie hires a cleaner to clean the house. It is possible for the cleaner to enter the house from the outside area F and walk through each room only once, cleaning each room as he goes and finishing in the outside area. Complete the following to show one possible route that the cleaner could take. So he's visiting every single vertex exactly once. Really important to notice whether we're visiting every single edge or every single vertex. In this case, it's just rooms, so every single vertex. So using this network over here, what's the route that he could take? And what we are trying to actually find in this case is a Hamiltonian cycle. Starting off at F, we can go A, B, E, D, C, and F. So that's a possible route. There's possibly other ones as well, but this is the one that I can immediately think of. Usually for these types of questions, there are multiple answers. So if you write it the other way around, that's fine as well. A, B, then E, then D, and C, and then finally F. What is a mathematical term for such a journey? We just mentioned this. It's a Hamiltonian path. So I'm not going to write it down, but it's a Hamiltonian path. And really important to recognize that it's a Hamiltonian cycle, not an Eulerian circuit. We are visiting every single vertex, not every single edge. Okay, and we just have one last question before we end the lecture. Consider the following graph the smallest number of edges that need to be added to make this a connected graph is. Okay, so we are basically trying to work out how many edges we need to add to make this a connected graph. Remember, a connected graph, the number of edges, that's not an E, is equal to the number of vertices minus 1. So how many vertices do we have? 1, 2, 3, 4, 5, 6, 7. So therefore, the number of edges that we need is 7 minus 1, which is 6. And we already have 2, so we already have 3. So we just need the remainder, which is 3. So that's the answer there. But yeah, that's basically it for this lecture in terms of content. Let's just quickly recap. Again, just sort of going over what we went through. So we went over number theory, so looking at the hierarchy of numbers. So we have natural numbers, integers, rational numbers, real numbers, and complex numbers. Just knowing what they are and how we can classify something. And just remembering the fact that complex numbers is the overarching sort of classification where it includes natural numbers, integers, rational numbers, real numbers. So everything is constituted by complex numbers. Another important thing to know is how to convert decimals. Remember, finite or recurring decimals can be converted to rational numbers. So just really remembering the process on how to do that. Then we looked at the different types of proofs. So we looked at direct proofs, negation, proof by contrapositive, all that sort of stuff. So just knowing when to use which type of proof is something that you will develop over time. But yeah, that's the different types of proofs, and we use the different types of proofs depending on what sort of question we're given. And over time, with practice, you'll really develop that skill to identify what proof to use and when. Then we looked at graph theory, so looking at the different features of graphs, looking at the different types of graphs. So we have simple graphs, connected graphs, planar graphs, isomorphic graphs, all that sort of terminology. I think in Specialist Maths 1, 2, it's not the terminology itself that is so important. Like, you'll never be asked, or draw a simple graph. It's more so the sort of understanding, and if you're given a question, just knowing what they're actually referring to, which is the most important part in terms of what you're learning in units 1 and 2. And like I mentioned at the beginning of this lecture, Specialist Maths, definitely a really challenging subject, but definitely really rewarding as well. And take unit 1 and 2 very slowly, try to understand everything that is thrown at you, because in unit 3, 4, you won't really have the time to do that. There's just so much content for units 3 and 4, a lot of skills that you have to learn and develop over the course. Units 1 and 2, I would just say take it slow. Don't try to be harsh on yourself if you don't get the grade that you want or you think you deserve. Remember, this is one of the toughest subjects in VCE, so just give yourself a pat on the back for even like choosing or thinking to choose this subject. It's really it requires a lot of courage, persistence, and dedication, as well as commitment. So it's not always about what your grades, like how good you are in maths. Like, no one is naturally gifted in math. And VCE has been designed in a way where it sort of considers that. It considers people that are not naturally gifted in math, and the curriculum is sort of developed in a way such that it challenges students enough so that they are willing to, work on what they know and work on what they're able to sort of get from the subject. So it's more so just about your persistence and dedication at the end of the day, not just about how smart you are in, a particular topic, or how well you are able to handle tests and exams or deal with that sort of pressure. So really, good luck for Specialist Maths. Really a challenging subject, but you will, at the end of the day, trust me, you will enjoy it. Either you will end up hating it at the end of the day and dropping out, at the end of year 11 and deciding to choose a different subject, or you will absolutely love this subject and continue on with units 3 and 4. Either way, just the thought of doing this subject is really courageous. But yeah, in terms of content, we're not really covering too much in today's lecture. The rest of the time for this lecture, I think we do have a few minutes, is just going to be Q&A. So I'll be monitoring the chat. Feel free to pop any questions through and I'll be answering them. So it doesn't always have to be related to specialist maths. It can be related to just VC in general or, uni or anything like that. So feel free to pop any questions through and I'll be answering them as they come.